if I gave you a curve in 3 dimensions, that looks like this. It says start here, and I described the curve for you with an R of t like over there. I would want you to be able to find the length of that curve. Or at least I would want you to be able to write down an integral that calculates that length. Integrals in general are really hard to solve. We know how to solve some of them. But I at least want you to be able to write down the integral. And then you could approximate the solution if you needed to. So I want to teach you how to do that. What you're going to do is you're going to take this curve and break it up into pieces. And on those pieces, you're going to just draw straight lines. And then we're going to approximate the length of this curve by adding up the lengths of the straight lines. And then after I do that for 4 pieces, how can I get a better approximation using a similar process? Think of how you did integration in the beginning. Use Riemann sums with rectangles, that represent an area. How did you get better and better approximations? Good, more rectangles. They got smaller widths. So we're going to do the same thing here. If you use more and more pieces, smaller and smaller lengths, you'll get better and better approximations of this thing because the error between the straight line and the curved piece will get smaller and smaller. That's the basic idea. So now let's talk about how to actually calculate that. So if I want the length of that blue curve, I'm going to approximate it by adding up the lengths of the green curves. And how can I calculate the length of a green curve? The length of one of these green pieces. That is the main idea to solving this problem. That's the main key for solving this problem. Okay, good. You can use the distance formula. So do you remember the distance formula?
Square root of x2 minus x1 squared plus y2 minus y1 squared. And since it's 3 dimension, y z2 minus c1 squared.
Good. This is how you calculate the distance between 2 points. It comes from the Pythagorean theorem. You can do the Pythagorean theorem in 2 dimensions to get a 2-dimensional distance, and then use the Pythagorean theorem again to get the 3-dimensional distance. We talked about this in relation to spheres as well. I'm going to call this delta x, and this delta y, and this delta z. Because as I use more and more approximations, these are going to shrink down. There's actually another way to represent this that I want to mention. And that is, since this curve is given by a vector r of t, and I know how to find the speed that point is moving along this, I can use actually rate times time equals distance. So this formula will work, but also what I'm thinking of here is I've got a setup where t is between a and b. And then the x's, y's, and z's, they all depend on t. So I've got, this blue curve is given by r of t equals x of t, y of t, z of t. All 3 components are functions of time. So if I just do rate times time equals distance, then I'm doing speed times delta t, where delta t, the change in time, is just the amount of time I'm letting go by between 2 points. Do you have an idea of how to calculate the speed using vectors? The speed of this equation? Okay, good. I need to take a derivative. If I take the derivative of r, a lot of times we represent that as v for velocity. And then that's a vector. How do I get the speed? So just the number that represents the speed. We're almost there. Okay, taking the derivative of x of t, y of t, z of t, that gives me v of t, which is another vector, right? It's still a vector, it's just that the components are the derivatives. But how do I turn that vector into a number that represents the speed?
Take the latitude.
Yeah, that's all I need to do. Good. So this sum is just the magnitude of v times delta t. That is my approximation. And as I choose smaller and smaller increments of this delta t, it gives me more and more pieces here that are shorter and shorter, get better and better approximations. What happens when I take the limit of that sum as delta t goes to 0? So I'm taking the limit as delta t goes to 0 of the sum of the length of v times delta t. And this should ring some bells from integration.
Take integral.
Yeah, good. It actually turns into an integral. This is just like a Riemann sum. This, you can think of this as a height times the width for a rectangle. So if you let the width of the rectangle shrink down to 0, you do get the integral itself. You know, we're saying t is going from a to b. And we've got magnitude of v times dt. So this is a quick way to say how we can calculate the arc length. I think this is pretty nice that it's that compact, because this is a complicated problem. I can hand you any curve in 3 dimensions, and you should be able to tell me how to calculate the length of that curve, and you can do it just like this.